question.
Sure. What's up?
So for me, we were doing the beehive thing.
The what?
And the beehive.
Oh, okay. Uh-huh.
And currently they're, sorry, I just ran up the stairs.
Uh-huh. Yeah. I understand.
So currently the hive, it's a 2x4 the hive sits there. There's
Yeah,
a beam that connects them.
Uh-huh.
And there's one of those like pylon straps.
Okay.
Secures the entire hive, the lid and all,
Okay.
to that bottom beam.
Okay. Uh-huh.
So in order to weigh it, we need to not put the straps on because you know what I mean? If we put the scale in between the bench and the hive, the straps would add extra weight.
Right.
Variable weight depending on how tight.
Exactly. Yep. Mm-hmm.
So we're looking for ways to secure. It's mainly the boxes. These are very, very heavy.
Mm-hmm.
So we're not worried necessarily about like the boxes tipping. The straps mainly the lid, which is only a couple pounds.
Okay. Uh-huh.
It's mainly to keep like raccoons and coyotes out.
Right.
But we want to make sure that like if a coyote like pushed it hard, that didn't tip over.
Okay.
That being said, I don't know if he said the doctor really said it could just be simple hand calculation, but I wanted to ask you too. What do you think would be the best option? Should I do like some statics? I mean, it wouldn't be static structural, right? It would have to be a dynamic simulation if I wanted to go that route, or I could calculate it by hand.
You could,
But it's not necessarily because there's a difference between just like a steady push and then like an explosive hit.
right.
So if something rammed it versus something trying to push it over.
Yeah.
So
I'd say I think probably hand calculation is probably the easiest. You basically just set it up like a
yeah, 'cause it's just the bench.
just a box, right?
Yeah, the box on the bench and then
You find the center of mass, and so the center of mass is going to be this way, right?
Yeah.
And so if something impacted from this side, I think you probably want to do it from a momentum perspective.
it definitely, I mean, just the worst case scenario would, because at the bottom wouldn't do much, so just if we're gonna do a point force or point impact, just at the top.
At the top,
Because if
it's
we
the worst case.
Because if we can handle it at the top, then we can handle it at the bottom.
Exactly.
Right?
So here's your pivot here.
Yeah.
So this is your moment. This one moment from this
So
one.
we'll just do it simple calculation.
I think that's probably the easiest.
And then just, I mean, I guess, I don't really know where to look, but just the guesstimate of how, of the average power of the hind legs of like a coyote or a raccoon or something.
Yeah, I think.
And then see if that has enough.
Yeah. I would. You can even do worst case. Like the worst case, because like a coyote is like an animal that hits it, it's going to crumple. Right? And so worst case, like they run full speed and kind of crumple, right?
Yeah.
And so you can basically take the worst case, or if you have like a rigid object hitting another rigid object, and so your time of impact is going to be really small, like something like 1 second or something like that.
Yeah.
And so the amount of force that's being applied there is going to be the momentum divided by the time. Right?
Yeah.
And so you apply that force here, and then you compute what's the highest force. That's
And then it makes it a little bit more complicated because the bottom boxes. The bottom boxes, so the height of the hives, or some bigger bottom boxes are about 60 pounds.
Yep.
And then normally the max it gets is about 2 of them. So that'd be 120 pounds, and this is about a foot and a half, right? And they have the little super boxes on top, which can go from 1 to 3. The most that we have currently at here are Fullerton, with the Arboretum, it's 1 right now. But these are only about a foot, and they're about 100 pounds. So even though it's taller, it's heavier.
Okay.
So you suggest just doing it like multiple times? Because I this one probably wouldn't matter because it's like it's wider than it is tall.
Yeah.
So like you'd have to do that would be too much, but probably like this one 120 pounds at 3 feet.
Yeah.
And then 220 pounds at 4 feet.
Yeah. I
So
think
just do that.
Yeah.
Maybe.
Yeah. Okay. I think that makes sense.
Because I don't know if it would, but then I don't know how much I want to like simplify it for the sake of accuracy, because this is definitely like
I think something like this. I mean,
because
you're
they can only stand up so tall.
Yeah.
Right. You know what I mean? Or
I mean, this you're already doing like a huge approximate. This is already like a huge task to take here too. So I think I'm doing something simple like this.
Okay. Awesome.
Yeah.
But yeah, no, so for the homework, that's like not just. I know you said keep everything the same, but then I kind of like talked through and demonstrated how you can't keep it the same. Is
Yeah.
that good? Or do you?
Yes. Yes.
Okay. Yeah.
Yeah. That's fine.
Yeah, because I didn't know if like because I made it work, with the other way. I thought you just wanted, I don't know if you wanted us to just stop, or I kept going to show you how, like, what I would actually.
Oh, yeah,
what
that's
hoops I
fine.
have, what else, but hoops
Yeah,
I would
yeah.
jump through to make it work.
Yeah, that's fine. Yeah, I think people did all different kinds of things for that one. So the important thing is it was more difficult. That's the point.
Substantially.
Yeah.
Yeah, also, I don't know what that other problem thing was. I think about too many elements
Mhm.
or something. My Ansys subscription just poops out.
Oh, okay.
It doesn't like it at all. So,
Probably it's usually too many elements.
yeah, 'cause my computer can handle it, but I don't know if there's like a certain upper limit that I need to like stay under.
Yeah, there is.
Yeah.
It's
Okay.
it's 32,000 elements.
32,000?
Yeah.
Oh, okay.
Mhm. If you go beyond that, then Ansys says you have to buy the full version. They only give you so much for free.
Yeah, that's fair.
Ansys, they let you, it's free to try, but if you want to actually do anything real with it, you have to actually
Yeah,
pay.
fork over that.
Which makes sense. I mean,
Yeah, I mean.
yeah.
Yeah.
Yep. All right, everybody, it's Ansys Day, and so if you want to go ahead and open up Ansys Workbench, and we can go ahead and get started once the lecture starts. The activity today is not as bad, and so I know activity 4 was kind of crazy, but the activity today is less because I know you guys are working on the midterm project as well, and so this one will take you less time, but it's also cool, and so that's kind of a. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everybody. How's everyone doing today? Good to hear. All right, so today we're doing another Ansys activity, and so today is going to be a fun one. And so we're going to be doing dynamics. And so kind of like what we talked about on Monday, we're very barely scratching the surface on dynamics. And so, I'm gonna warn you that probably one thing that might be confusing today is you're going to see a whole bunch of settings and a whole bunch of parameters that that probably won't make sense just because we haven't had the time to cover it. But I will show you kind of the bare minimum of what you can do with dynamics, right? But even with the bare minimum, you can do something cool. And so basically what we're going to be simulating today is a car crash, right? And so we have a car chassis here, or at least a decent facsimile of one. And we're just going to be ramming this into a brick wall, or in this case, a structural steel wall. And then we're going to see what happens to the car, right? So I think it's a fun activity just because it's the only one that we're doing that involves motion. And you'll actually be able to see a video at the end of it too. And so you'll be able to see the video of the car actually hitting the wall and it's bouncing back and all that stuff. Okay. But also kind of like what I said on Monday that, I wouldn't probably consider this to be the most realistic example because we're assuming linear dynamics throughout this whole time. But normally if you have a car that's going to crash into the wall, you're going to have a lot of nonlinear buckling and a lot of, parts getting destroyed. And we won't be able to see that. And so it'll almost kind of look like a jello car hit a wall and it's kind of jiggling back and forth. But, I think that's also kind of is fun as well. Okay. All right. And so let's see, besides that, activity 4 is due tonight. Right. And so make sure you're working on that. I know there's kind of been a lot of issues with the shells and beams and the contacts and everything. And a lot of people are getting solver pivot warnings. So if you're having issues with it, definitely reach out. I do have plans right after the lecture today, but I'll try to go back on my computer when I get back, just to kind of answer any last minute questions. And so, I'll make sure you work on that. And this activity, just because I know next week is going to be the, oh, actually I meant to put this further back. So just because I know next week the project is due. And so I'm going to push this back until Friday, November 5th. Okay. And so this activity will be due in a little bit over 2 weeks, so 16 days. And so I know it says Wednesday, November 3rd here, but I had planned to push it back to the 5th, but I think I just forgot to do it. Okay. All right. And so are there any questions I can answer before we get started? Okay. All right. And so let's go ahead and get rolling. All right. And so for the activity today, we have just one CAD file. And so if you go to the Ansys, if you go to the Canvas website, you can go ahead and download this. And so it's an IGS file called car crash analysis. Okay. And then we're going to open up Ansys. And actually, let me start from scratch just so you can see. Okay. Right. And so when you open up Ansys, normally what we do is we do a static structural analysis, right? But today we're not doing statics. Today we're going to be doing dynamics. Okay. And remember what we talked about on Monday, that there's two different types of dynamic analyses you can do within Ansys. And so you can either do explicit dynamics or you can do transient structural. Okay. And remember, the big difference between them is, you're gonna pick explicit dynamics for situations where you're gonna use a very small time step size. Okay. And so for phenomena that are gonna happen really, really quickly, where you need to capture with kind of a small time step size, you're gonna use explicit dynamics for this. Okay. And in our situation here, where we have a car crash, right? The car is going to make impact with this wall in a very small amount of time, right? And so this is not something that's going to happen in slow motion. And so because of that, we're going to be using explicit dynamics. Let's go ahead and double click that, right? And so here we have our explicit dynamics, analysis type here. And just like we always done, let's go ahead and load in our geometry. So let's right click geometry, go to import geometry. Let's go to browse. And go ahead and locate the car crash analysis.igs file that you just downloaded from Ansys or from Canvas. Right? And then we can go from there. Okay, so don't open model yet because we have to create some new material property data. But just go ahead and import the geometry into Ansys. Okay. All right. So was everyone able to? Everyone caught up? They open up Ansys Workbench and they've imported the geometry. Okay, and so before we jump into mechanical, let's go ahead and load in our material properties. And so let's double click on engineering data here. Okay, and you can see by default we have our just regular old structural steel. Okay, and so for this analysis, I want to do a car crash with two different materials. And so I want to do a car crash with an aluminum car, and also a car crash with a plastic car. Okay. And so, for the first time, I think for the first time in this class, we're going to use the materials from Ansys's built-in library, right? And so we're going to click on this button right here called Engineering Data Sources. Okay. So let's go ahead and click that. Right. And so you can see here we've opened up the general library of materials within Ansys, right? And so the way that this library works is that in this top window right here called Engineering Data Sources, there's lots of different categories of materials that we can choose from. Okay. And so if we read down the list, we can see we have this Ansys Granta materials data for simulation. So this is only a sample. So I think this is only a subset of all the materials that are available. Okay. And so you can look and see what materials are in these libraries by just clicking on them. And then you can look at the materials that are here in the middle window. Okay. All right. But we don't want anything from here. And so the category that we want is just general materials. And so let's go ahead and click on general materials here. Okay. And then the materials that we want to add are aluminum alloy. Okay. And down there, we're going to also add polyethylene. Okay. And so adding a material here from the library is really simple. And so the only thing you have to do is click on this plus arrow right here, or this plus button. Okay. And so when you click that, okay, you'll notice that it disappears, or it doesn't disappear. So you'll see that there's a book next to this list, right? And so that tells us that we've added aluminum alloy to our project. Okay. And so go ahead and do that for aluminum alloy. And then we're also going to do that for polyethylene as well. Okay, so let's go ahead and scroll down this list and go down to P. Okay. And so you can see here we have polyethylene. Let's go ahead and hit the plus arrow for that. Okay.
And polyethylene is one of the plastics that that Ansys has kind of loaded by default. Okay. And so we're going to do a car crash for an aluminum car and a plastic car. Right? So that's basically what we're going to be doing. Okay. And so to check to see if you loaded your materials right, you can go back up here and click on engineering data sources. Okay. And then it's going to return to your list of engineering data. And you should have 3 materials here. So you should have aluminum alloy, you should have polyethylene, and you should have structural steel as well. Okay. All right. So was everyone able to load in the material properties for the for this activity? Okay.
Yes.
All right. And so if you if you've successfully added the material properties, let's go ahead and close the materials tab. And then let's double click on model. And so now we're going to open up Ansys Mechanical. All right, so there's the pop-up. Right. And so after you load in Ansys after you launch Ansys Mechanical, you should be greeted with your car crash geometry right here. Okay. All right, and so you can see our geometry is basically right before our car is hitting the wall, and so it's it's a photo taken right before disaster, basically. Okay. And so before we do anything, let's go ahead and assign a material to our car. Okay. And so if you open up the tab for geometry, you can see we have 2 parts in our assembly. And so if you click on part 2, you can see that part 2 corresponds to the wall. Okay. Whereas part 1 here corresponds to the car. Okay. Right. And so before we move forward, we have to assign a material for each of these parts. Okay. For the car, we're going to assign aluminum alloy. So let's go ahead and click part 1 and assign this as aluminum alloy. Okay. And in fact, you can rename this too if you want, just to make it a bit more clear. So part 1 is the car, part 2 is the wall. Okay. So for the wall, we don't really care what it's doing because that's not the point of the analysis. And so we can just leave the wall as just structural steel because the wall is not really going to be doing much. It's only just going to be there just to have something for our car to collide into. Okay. All right. And so once you've assigned properties to the car and the wall, the next thing we're going to do is we're going to remove a connection. Okay. Right. And so if you go under contacts or connections and you go to contacts and you click on this contact region, you can see that we have a contact region between the car and the wall. Okay. And so Ansys created this by default because of those 2 parts are in very close proximity. But in this particular case, because we're simulating a collision, we want the car to be able to hit the wall and come off. Okay. And so to do that, we actually have to delete this contact region here. And so let's go ahead and right click on contact region and let's go ahead and delete this guy. Okay. Right. And so that's going to make it so that now these two parts in our assembly are going to be decoupled, right? And so now they can separate, they can move relative to each other, they can be free. Okay. All right. All right. Any questions? Any questions so far? Okay. All right. Next thing we're going to be doing is the mesh. Okay. And one thing you'll notice right away when you click mesh, that the element order has automatically been assigned to be linear, right? And so, this is one of probably the only case in the class where we're going to be using linear elements. And the reason we're using linear elements here is because dynamic simulations are a lot more expensive and so they take a lot more time to compute, then Ansys kind of default sets it down to linear elements just to make sure the cost doesn't get too crazy. Because with quadratic elements, the cost can go up actually quite a bit. And so unfortunately here, we're going to be limited to linear elements, but that's okay, right? And so the way that we're going to get around this is we're going to basically make sure that our mesh is refined enough in the car in order to get reliable results. Okay. And so let's go ahead and create a sizing object for both of the wall. Okay, so let's go ahead and select the entire wall. And then let's go ahead and insert a sizing object for the car as well. Okay. And let's set mesh sizes here that are that give us a good result. Okay. And so for the car, the car is going to be the main object of our analysis. And so let's make sure that our mesh size for our car is sufficiently small. Okay. And so I'm going to set the mesh size to be, let's say 5 millimeters. Okay. And then for the wall, the wall, we don't really care about what's happening there. We just needed to mesh. And so we can go ahead and put a coarse mesh right here. And so I'm going to put a mesh size of 25 millimeters. Okay. Okay. And so that's the bare minimum of what you need for this mesh. Okay. But if you want to change the shape of the elements on the car, or if you want to add some refinement, you're definitely welcome to do so. But for just kind of this demonstration's purposes, I'm going to just keep it as this. Okay. And so after you're done producing the mesh, you can see that the car is relatively has relatively fine mesh associated with it. Okay. It's a tetrahedral mesh, in fact. Okay. And then for the wall, we have a pretty coarse hexahedral mesh. Okay. And the total number of elements here is we're kind of pushing it already. And the total number of elements is 28,313. Okay. All right. Any questions on this?
What was the sizing on the car?
The car I use 5 millimeters, but that's just for me. And so you can use a different size if you want. Yeah. With 5 millimeters, it is going to be a little bit expensive, and so when you hit solve, it's going to take a bit of time. And so if you want to get to the results sooner, you can mesh it with a coarser mesh. And so something maybe on the order of like 7, 8, 9, 10 I think is fine for this too. Okay. All right. And so the next step is to add our constraints. Okay. And so what we want to make sure is after the car hits the wall, we want to make sure the wall itself doesn't move. So let's go ahead and fix the wall. Okay. So let's go ahead and insert a fixed support. Okay. And we can fix this wall in a lot of different ways. The only way that you shouldn't fix it is you shouldn't fix it on this surface right here, right? Because this surface is basically going to be the surface which is going to be contacting our car. And so we don't want a fixed constraint basically right next to where an impact is going to happen. Okay. And so you can either fix the wall, you can either fix it from the back right here, right? That's fine. Or you can fix it from all the sides of the wall, and that's fine as well. Okay. And so that's what I'm going to do. And so now this wall is fixed from all the sides. So I chose it like this just because I feel like this is kind of a more realistic way to fix it. Because if this wall, more than likely, this wall is going to be part of some much bigger brick wall behind it. And so by fixing it on the edges right here, that basically gives the same effect of this wall being attached to something else. But if you fix it on the back side, that's fine too. I think you're going to get the same results. Okay. All right. And so that's the fixed support on the wall. The last constraint that we're going to do is we're going to be doing a roller support on the car. Okay. And so basically what we want to do is we want to make sure that the car stays the same height. Okay. And so this is kind of just to make sure the car doesn't, when it crashes, it doesn't go into the ground. Okay. It's not going to be the most realistic thing because realistically the car can kind of go upwards, and some cars do that when they crash. But this is something we're going to do to mostly limit the cost of the simulation to make sure that we get a consistent converged result. Okay. And so let's go ahead and add a displacement boundary condition. And then I'm going to select all of the lower surfaces of the car. And so you might have to rotate your car on the backside. And we're going to select all of these surfaces down here. Okay. And so you should have about 8 surfaces in total. Okay. And we're going to set the y component of the displacement to 0. Because the y direction is going vertically up in this case. And so we want to make sure the car doesn't displace in that direction. Okay. And so now literally the car is going to be on rollers heading towards the wall. All right. All right. Any questions on this so far?
Yeah, Professor.
Yep.
You said just select the whole lower rim.
Yes. Yeah. You might have to zoom in a little bit just to make sure that you can click it.
Because I'm getting like several different surfaces from my wheel.
Yeah. There should be 8 different surfaces, and so you have to hold control and click hold them. Yeah. Okay. All right. So those are the constraints we're going to put on the simulation. Okay. So normally at this point we also add loads, right? And so our static structural simulations they're not complete unless we do constraints and loads. But for this particular simulation, we're not going to put any loads in this case. Okay. And so the driving force in our simulation here is actually going to be done through a velocity. Okay. And so we're going to give the car basically a velocity heading towards the wall. And so we're going to give it a negative x velocity. Okay. And so, if you go to the project outline on the left, you'll see that there's kind of a new entry here that was created that's not usually there in our static analysis. Okay. And that's called initial conditions. And so initial conditions, they basically define the behavior of all of the bodies in the simulation at t is equal to 0. Okay. Remember the whole idea with dynamic simulations is that they're going to be advanced forward in time, right? And so in order to do that, we have to define what everyone's doing at the beginning of the simulation. Okay. All right. And so just like you normally do for boundary conditions, you can right click on initial conditions here and you can go to insert. Okay. And you can see here that we can create 3 different initial conditions, right? And so we can give something a velocity, we can give something an angular velocity, or we can give it a drop height. So for this particular case, the initial condition that we're interested in is velocity. Okay, and so let's go ahead and do that. And so with this, we're going to supply a velocity to the car heading towards the wall, right? And so let's go ahead and select the entire car body and go ahead and apply that on the geometry there, okay? And then let's go ahead and define the velocity in terms of components. I'm going to switch back to meters per second. Actually, keep it in millimeters per second, okay? And then we're going to give the car a velocity in the negative x direction, right? And so, just to start out, let's do minus 50,000 millimeters per second. Okay. Right. You want to make sure that your velocity here is negative, because if it's positive, then the car is going to go the other direction, right? And so if you look at the coordinate axes here, a negative x velocity means that the car is going to go this way towards the wall, and that's what we want. Okay. All right. Okay, and so that's fine. And so we're not going to supply an initial condition on the wall, because all the wall just has to do is just sit there. And so, it doesn't have to have any velocity or anything like that. Okay? And so the only thing we need is just for the car. All right. Any questions on the initial conditions? Okay. All right. And so we're almost done. Okay. And so the next thing we have to specify here is the time step size and also the ending time step. Okay. Or specifically, we only have to specify the ending time. Okay. And so this is basically going to specify how long or how much time we're going to be simulating for. Okay. And so when you're specifying this end time parameter, you basically want to specify it so that you capture all of the behavior that you want to capture, okay? And so if you expect your dynamic situation to occur over the span of, let's say, 10 seconds, then you should set 10 seconds here, okay? But we don't need 10 seconds here. And actually, in fact, our car crash is going to happen so quickly that, you know, we don't need to add that much time here. And so if you want to, and so basically anything less than 1 millisecond here is fine. And so if you want to do 1 millisecond, you can do 0.001 seconds. Okay. Or if you want to, but even that might be a little bit too long. And so if you want to make it even less than that, you can do 0.00075. Okay. And so that's the amount of time that I gave for my own simulation. Okay. Right. And so if you, if you want to read the rest of these settings here, it's going to be a lot of gibberish. And so, there's a lot of settings here that we're just not going to have time to cover. But the one thing I did want to draw your attention to was the time steps. Okay. Okay. And so on Monday, we talked about this idea of the time step size as, as an important parameter that Ansys has to specify in these dynamic simulations. Okay. If you don't specify anything, then you're basically going to let Ansys determine these for you. Okay. And most of the time, Ansys actually does a pretty good job of selecting these. But if you want to have more control and you want to set the time step size, you can do so here. Okay. And so the reason they specify it, they let you specify initial, minimum, and maximum, is that Ansys uses what's called a variable time step algorithm, where during the simulation they actually adjust the size of the time step, based on the physics that's happening, right? And so if there's something really, really important happening, then Ansys will smartly kind of make the time step size smaller and smaller, okay, up until you hit this minimum amount. But if nothing really interesting is happening, then Ansys will kind of smartly increase the time step size, right? Thereby decreasing your cost and making it so that your simulation is more efficient that way. Okay. But if you don't have any reason to change these, then you can kind of leave them as the defaults for the and let Ansys choose. Okay. All right. So last thing we're going to do before we hit solve is we have to define our results. So let's go ahead and add a total deformation. Let's go ahead and add a equivalent strain and then equivalent stress. Okay. Okay. And then once you have all that, you can just go ahead and hit solve. Okay. Right. And so this process is going to take a while. And so, this is you're probably going to be waiting here for a few minutes. And so if you want to see how your simulation is doing, the progress bar is here in the bottom left. Okay. Or another cool thing that you can do is you can actually view different metrics for your simulation happening in real time, right? And so I'm going to go ahead and click on this entry right here called solution information. Okay. Right. And so this will basically let you monitor your solution, as it's going. Okay. And so right now the default is this thing called solver output. Okay. Or solver output right here. And so this is kind of the raw, text output that that Ansys is putting out. And so this for 99.9% of people, this is absolutely useless. And so I don't know why they make this a default, but you can go down here and you can change this. Okay. And you can see, different metrics for your simulation. Okay. And so I'm going to go ahead and click on energy summary. Okay. And then what you're viewing here is a view of how the energy in your simulation is changing over time. Okay. And in particular, you'll see that there are two main curves here. And so there's a purple curve for internal energy and a blue curve for kinetic energy. Okay. Right. Excuse me. And so as the simulation goes, you can see that the kinetic energy is going to go down and then up. And then the internal energy is going to go, it's going to start low and go high. Okay. And so what's happening here is that at the very beginning here, right, remember at the very beginning of the simulation, we specified our car to have a certain velocity, right? So we gave it a velocity heading towards the wall. And so because of that, all of our energy and all of the energy in our system was purely kinetic energy because it was motion, right? And then after the car hits the wall, then the car is going to start to slow down, right? Because it's hitting the wall, right? And so the kinetic energy in the system is going to go down. Meanwhile, after the car impacts the wall, the car is literally going to start crumpling on itself, right? And so the car is going to be deforming. And so as the car deforms, all of that kinetic energy is getting transformed into internal energy, or as some people like to say, it's being transformed into strain energy. Okay. And so you can kind of see the amount of energy in your system changing, and that's really cool. Okay. And so for a normal car crash, once we kind of go down here, then it usually doesn't go back up as much. It might bounce back up a little bit, but you can see in our simulation here that these cars actually bouncing back up quite a bit where they get its full kinetic energy back. Okay. And so what's happening here is that the car is actually bouncing. It's actually it's hitting the wall, it's bouncing, and then it's bouncing back, and it's kind of acting like a piece of jello or a spring. Okay. And you'll be able to see that in the animation that shows up afterwards. And so we're almost done here. And so we're just at about 98%. Okay. And so once the simulation finishes, you can see that this is the time history of the energy in your simulation. Okay. And so if you want to view the video of the results, you can click on any of the results. Okay? And so I'm going to look at the total deformation. Okay. All right. And if you want to play the results, you can go ahead and click on this little play button down here. Okay. Right. And so you can see the car is hitting against the wall, right? And so you can see that, it's getting all of these little vibrations and everything. It's doing all this kind of oscillating stuff. And so, a real car, if you hit it against the wall, it's just gonna crumple. And so, this is kind of a linear approximation of that car crash. But you can actually see that, we're actually simulating a dynamic situation here. Okay. All right. So was everyone able to get to this point with the animation? All right, and so that's all there is to this activity, actually. So I promise you that it would be shorter than activity 4, and we're done in about 30 minutes. And so the rest of the activity basically is going to be just kind of playing around with this a bit more, okay? Mostly in playing with the initial velocity. Right? And so in problem 5 of the homework, basically what I want you to do is assuming that the yield strength of aluminum is only 55 megapascal. Okay. Okay. And so assuming that the yield strength of aluminum is only 55 megapascal, I want you to find the maximum velocity that this car can hit the wall at and still not yield. Okay. And so if we go to the equivalent stress right here, right, you can see that the equivalent stress right now, the maximum, is 920 megapascal. Okay. And so you can see that under this velocity configuration, this car is not only going to brake, it's going to super brake. And so, I want you to basically lower this velocity and try to find the maximum velocity that you can do to get the maximum stress under 55 megapascal. Okay. And so you don't have to get it exact. And so, because I know these simulations take a few minutes to run. And so as long as you're getting into the ballpark, and so if you're able to get a stress like around 50, between 50 and 60, I'd say that's close enough. Okay. And so that's problem 5 of the activity. Okay. And then problem 6 is I want you to repeat the analysis, but I want you to change the material of the car to plastic. Okay. And so a plastic car only has a yield strength of about 5 megapascal. Okay. And so I want you to do the same thing where you find the maximum velocity a plastic car can use to hit the wall and still be in one piece. Okay. All right. Any questions on that? Okay. All right. And so I'm actually really thirsty, so I'm actually going to run out and get a drink of water. But after that, I'm going to go walk around and just kind of check how you guys are doing. Okay. And so I'll be right back a couple minutes. And then if you have any questions, just flag me down. Let me play this in a second.
Okay. Okay. The only difference that I think is the size. So this is fine.
Yeah, okay. Yeah, I think so with dynamics animation, because we're using linear elements here, it's going to be really sensitive to the mesh. And so with 5 millimeters, like the main thing that's happening right now is like we're getting shear volume because we have linear touch. And so the smaller you make your elements, the better is for shear volume. And so for your cases, you're using, I use 5 millimeters, you use 4. And so there's less shear. So that's fine. And so, so this is another one of those activities where it's kind of this educational. So I mean, and this is pretty far from reality. But cars not going to be this. And so if you want to get the same as mine, you can use 5 millimeters. I think this is more.
It's more.
Yeah, it's more. Yeah. You have a question? Oh, okay. Okay. Sure. Sure. Yeah. It says right if you can get it for this. I mean, we're making assumptions and interpretation, but this is good. Oh. Oh. Yeah, sorry, I couldn't make it. There was a lot of people. I really struggled. Yes, the recording will be updated or something. Right, you probably the same policy.
So I looked at pages. Yep. You changed it. It looks like you changed the wrong word.
Yeah.
Yeah, I think it is moving. It's just it's moving. It's moving just so little that it's
Is it like so little that I can't see it? Or
just you can emphasize what it is. Right now it's true scale, so you can emphasize that. So you can make it.
Like space can extend the rope surface.
Okay.
To meet so it seems when I open it's not touching all.
Did you
I tried to like update it. It still doesn't.
oh so did you close the mechanical before you?
Yeah.
You have to close mechanical.
So, but when I open space again, the model is already like extended in space. Right?
So it's already extended, but then you open up there.
Yeah, it's extended. If I open model again, it's not. Extended. It's touching. Good changes. And another thing that I found that was like trying to solve a solution that the elements is like 60,000 mechanical hash. Yeah. So now it is like
Oh, I see. It might hold on. Yeah, 60,000 is kind of.
so I'm not still yeah, strange.
Yeah. So when the first time you extended it, it didn't ask you to update. It didn't ask you to update what it said. I guess
Usually when I reopen English pass them back to reuse.
Yeah.
It's not
Nothing.
It happens after the mechanical structure. So I think it might be it because during the breakdown there's a organization there's a file CADR
Okay.
It's a crash.
Oh, I see. I see.
So,
Yeah, maybe it's related to that. Because I guess it crashed. Maybe it can't leave the payment stream. You can try to relaunch just the entire Ansys workbench, like save the project and just relaunch the workbench. But if that doesn't work, it might have been some connections in the project might be broken. So you might have if you want to do it, you have to kind of restart it from scratch. Make sure that all the file dependencies are there. So that's kind of, I'll leave that to you. I think if you're able to explain basically the mesh convergence why that's happening, and have this as a reader, with adequate explanation, that'll be
so should I bear in mind that the developments should not exceed like a certain amount?
Yeah, so the limit, so for if you're doing it on your laptop, the limit is 32,000 lines. On here, I think the limit's a bit higher, so it shouldn't exceed 60,000. Usually it'll just stop you. So usually it'll say that there's too many limits, and then it will say you can't run it. But I do know these computers are powerful, so there might be some where we're just the computers itself are not doing so. These computers are scheduled to be replaced next summer, so these are kind of like so it could be just that it just overloaded the RAM with this. Okay, which is unfortunate.
I think I'll read it.
Okay.
Sure.
Okay.
Thank you.
Yeah, Tristan, I was kind of experiencing the same thing. So I switched, I just switched over to hexes, and actually my element count went down way a lot too. And so, yeah, I think something like that. Did your element shape change to hexes? Or is it tetrahedron in both? Or tested? Yeah, it's probably something as what you're describing, because there might have just been some areas where they kind of just jam pack some elements in there. So with the bigger size, it created some kind of awkward pockets where it had to kind of really fill that in with a lot of really small tets. But with the smaller size, it's able to kind of fit all of those edges kind of, exactly. Yeah. Mhm. How's everybody doing? For a minute. These simulations do take a while, and so it is kind of a lot of downtime, just changing velocity, hitting go, and then just kind of waiting for it. So, but I figured this would be kind of a good time in the semester to have this activity because there's not too much else going on with the activity, so kind of gives you flexibility to do that stuff.
So this is the screenshot from the definition before the thing.
Oh,
So I can show it to you right now because it's fresh. So I'm so there's a little bit of like the surface of the road, like tip a little bit.
Yeah.
I'm pretty sure that this is when it fits the what is applied. So I'm wondering what's the reason. Like, this-
Yeah, it is. It does look really strict. So I think what's happening is that this side of the road, by the way to it, is kind of dipping down so much that it kind of makes a really high slope. And so you can see it's blue, and so it's technically not conforming. So I think it's because of the down here, then this part right here dipped down so much.
because the middle part.
Exactly, right. And so and also by default, Ansys will exaggerate the deformations. And so it's like, in fact, it makes it seem like it's technically like that, but it's actually not. Because of
Yeah, so actually it's not dislocated.
Right, yeah, it just looks like, because it's just right next to it, it's dipping down so much. And so you have almost like and so it's kind of, you know, and if you look here, it actually looks like it's separated there. It's just a rendering. Right down here, that's why it's dipping down so much.
So it's kind of like a visualization.
Exactly, yeah, it's a visualization, it's a visualization.
So after the road surface like is touching to the side, I think this screenshot of
Yeah. That's
My convergence test didn't really want to convert.
that happens for some people, so
Oh, yeah.
it's okay. This is pretty converged.
Okay.
And so
I
you're looking like,
did say that it looks somewhat converged around the EGME.
yeah. I mean, it's still, I would say it's converged probably right. Yeah. And so there's always going to be a little bit of, so it's never going to be exactly the same. That's going to be really hard to do. So there's always going to be a little bit of wiggle, but it's about, you know, how much wiggle is it relative to here? Because you started with like over 1 right here, if you dip down, it's like 0.7. And so here, I'd say it's still fluctuating quite a bit. But, you know, once you reach here, then the fluctuations get much more. So I'd say around here, you're pretty much with that, and that's the convergence point that I got to around 50.
You're straight up just stopping the X1 down next
Thank
to.
you. I don't know why I imagine it have to be like straight up.
That ideally it would be, but it's never. So there's always gonna be a little bit.
Okay, sounds good. Thank you.
She does need X1 and X2 is the 1/2 and 2/2.
Actually, yours is like perfect thing to be like because mine does not run until like around 40 or 50 years. Because I like I applied because of value correction. So professor said the more knowledge you apply, the more.
But the thing is, dude, if
Oh, yeah,
she was
fine.
on it was like an
It's a weight
exam,
of the car
she was
and
like
then put like
determined the
some weight
Yeah.
on the face.
I also put the stand.
Oh,
But yours like it's complicated.
No, just like I was doing it earlier.
I do that sometimes.
I just started pulling this up on Flex Studio, Flex early. And now because it's like, dude, I've been fucking, because when I'm in bed, I can feel my right hand getting more comfortable.
Even
Because I think I'm shifting over this way. Yeah. So like I'm always just like, okay, my right one bigger, the other left one small. No way.
even though
Fitness 19. That was my first gym I ever went to. I mean, not here.
I haven't really taken the time. I got that. I paid 1999 that everyone. And I had that like 13. So. Yeah.
I'm actually doing text on like.
Something over there. And then they're like, sure, I'm gonna take one.
I'm not, I. Yeah.
Wait, you didn't say anything in like the lead up to the site?
Like I'm new, right? So
Often it's trying to enforce it inside this here. I would say,
Yeah, I've never seen a single person ever go up there.
yeah, I'll try myself. I don't know. Another one of those. I'm not gonna be- Yeah, I'll start.
Yeah.
I'm not sure.
So the hex is on and I go around for a while. It's peak out, like that, but it's just kind of not. It just comes to some. And they're like, you can't talk to me. Like, feel free to find stuff to do. And like, and like, you know, like, so you can't talk to me. That's a kind of fuck.
Yeah, but then like the risk of getting a car like that, so is they can fuck up that. Kids, obviously.
Yeah, he was like
that.
that. Yeah, and I know everyone's busy.
Okay, yeah, that's fine. So the hex longer thing is just a little bit. Even I can't get to it.
So did you actually figure out? Yes. Okay. Explain it to me in plain English. General terms.
Nice.
But this is not confusing. It's basically the same. It's basically the same.
I never used it before.
I'll have to look over.
Because that property of like. That's so frustrating.
Basically saying.
It's not like-
Weird thing is. Two by two is what you want to find three of them. Yeah, that's gonna be fucking.
Come on, don't be it. I'm not there yet.
So basically, what you're gonna want to do.
Hold on.
Velocity's constant. That solution.
Yes, that's just always.
Oh, for him.
Dude, I don't even have articles.
Just showing you that. Makes sense.
I think it's probably just the inertia. Like right before the part accelerated, and right before you kind of have this, like right before you jump up. You treat it as kind of like it's technically a dynamic situation. So we treat it as like this right before. Yeah, it's a good question. Actually. But I know you can use a cheat. I think some of those constraints.
Also, so for meshing, I found that like when you're assigning for method, there
You have to do the whole body.
there's whole ones, but when we're using sizing, we can use like correct, we can use the faces or like edge stuff. There's a difference that I noticed is that when I use notice sizing selection makes big it's different stuff that use edge for the beam state. It give me the options of dimensions and set. So when I choose the beams with body, I do not get number of divisions.
Oh, interesting.
So is there any preference to like choose the sizing to be from bodies or
It's just personal. So I think with this one, because it's just a bond, you can basically define how many divisions you want in there. So if you want to do it, sort of that's fine too. But me personally, I do everything just. But it's personal preference, and so you can kind of get whichever one makes sense.
so I can choose the beams either from bodies.
Yeah.
And there would be a control to choose like the beams sizing for the methods for
Oh no, yeah. So for the method, you always have to choose body just because it's it defines basically the whole length. Yeah, the reason you can do sizing for edges and faces is because you can define like a local size of just the face, and then and have that modified to the rest of the body too. But for the method, you kind of have to do it. So but for this one, since they're 2D and 1D services, then there's
just
All right, guys, it's about 6:45, and so that's the end of class day. So of course, you guys are free to work here for as long as you want. Just the usual policy. If you're the last one here, just close the door and then turn off the lights. But thank you guys for coming today. Remember, I'm going to be out of town this weekend, and so if you have questions on the project, if you can get it to me by tomorrow, I'll give you an answer. But Friday until Sunday, I'm not going to be available. Okay. All right. So have a great weekend, everybody. If you have questions on the project, definitely let me know. And then I'll see you guys next week. Question for absolute max. Yes, yeah, you can get it from the tabular data. Absolutely. Yeah.
The mesh comments do have to do this.
For this one, no. Yeah. Okay. Sorry. One more thing, guys. So on activity 5, there's a part where I say you have to do a mesh convergence test. You don't have to do that, and so you already have made you do one for activity 4. And actually for this one, it's going to be a lot harder because the simulations take more time. So don't do the mesh convergence test. I think it's
Convergence test?
yeah, and so I think it's right here. And so I forgot to take that out. So I'll send an email to tell everyone that you don't have to do that for activity 5. For activity 4, you still have to do it. For activity 5, no mesh convergence test.
Take 5 years.
Wait, what? It would take 5. Yes.